Good afternoon, everyone. We are back with Algebra 1. We're in section 3.3 of our text from Bob Jones University Press. We're going to be discussing negative exponents today. First, however, we've talked a lot about why does the chicken cross the road, why does the dog cross the road, why does the armadillo cross the road. I don't know what all we've said. Can you tell me why it is that the turkey was afraid to cross the road? The pilgrims were on the other side. And then, do you know what happened when Humpty Dumpty fell off the wall? Well, all the king's horses and all the king's men had scrambled eggs for dinner. Now, in honor of all of you Texas A&M fans out there, I am going to write in orange today. Go Longhorns. And then I will know how many of you have actually watched this video and how many of you are UT and how many of y'all are A&M. So, negative exponents is what we're going to be talking about. And back at the beginning of our text in chapter 1, we saw how using exponential notation was just a way to show repeated multiplication. If we have something that looks like this, 2 with the little 3 up to the right-hand side of it, this is called exponential notation. The 2 is called the base, and the 3 is referred to as the exponent. And what this tells us is probably that I'm writing too high. What this tells us is that the base is used as a factor 3 times. So when you're evaluating exponential expressions, you use the base as a factor as many times as the exponent is. And of course what you're going to see, and what you will use a lot in algebra, is the fact that your base is not going to be numerical. Rather, your base is going to be a variable. And there are 2 forms. It should be pretty obvious to you at this point that if we have a cubed b squared, what does this mean? Well, this says that we're using a as a factor 3 times and b as a factor twice. So this is what they would call expanded form. And with the exponents, I bet you'd never guess what they're going to call it. Yep, that's right. Exponential form. So when you have questions that they're asking you to give an answer for, exponential form means use exponents. Expanded form, they'll probably only ask you those questions just a couple of times because this is a much more cumbersome method of showing multiplication of variables, and they just want to make sure that you understand what exponential form is actually saying. There are the properties of exponents that you learned in chapter 1. You're also going to use these with variables. What I'm going to do right now is write down these definitions or these properties, and you have simply got to know that if you're going to multiply exponentials, you add the exponents. If you divide exponentials, you're going to subtract the exponents. And if you have an exponential raised to a power, what you do is you multiply the exponents. That anything raised to the 0 power is 1, regardless of what you have. So, let me see how high I can go. Right there. Okay. If you have two exponential expressions here that have the same base, different exponent, you add the exponents, x to the a plus b. If you have exponential expressions that you are dividing, whether or not it's written like this, or if you have it written in rational form, x over a divided by x over b, you add the exponents when you're multiplying, you're going to subtract the exponents when you divide. And is that going to give you a negative exponent sometimes? Yes, of course it is. If you have x to the 4th divided by x to the 7th, it's going to be x to the 4 minus 3, x to the 4 minus 7, which will give you a negative exponent, which would be x to the minus 3. And you're going to see how we deal with those. If you have an exponential expression that is raised to a power, here's your exponential expression. It's going to be raised to a power. You're going to multiply those two exponents together. This becomes the product. This is called the product rule, quotient rule, quotient rule, power rule. This is an exponent that's raised to a power, so we're going to call this the power rule. Also, if you have any algebraic expression here, any algebraic expression that is raised to the 0 power, that answer is going to always be equal to 1. It doesn't matter if you have x squared y cubed z to the minus 3 divided by ab to the 7th c. All of that in parentheses raised to the 0 power is going to be equal to 1. So this right here would be how exponents work with variable expressions, and they're just showing you in your book some examples of how this actually works out with numbers. 2 to the 4th times 2 squared is 2 to the 4 plus 2, which is 2 to the 6th. So some of you, when you were working with your homework, if it was 2 to the 11th times 2 to the 7th, you'd write out 2 times 2 times 2 times 2 times 2 times 2, to come up with your answer. These exponent rules work for numbers. This is 16 times 4, which would be 64, 2 to the 6th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. One more makes it 2 to the 6th. 32 times 2 is 64. But this is just using our exponent rules for products. Specifically the product rule for exponents, 2 to the 4th times 2 squared. You add the exponents together, 4 plus 2, gives you 2 to the 6th. Now if you have something that you're going to 2 to the 5th divided by 2 cubed, simply subtract the exponents. 2 to the 5 minus 3 is equal to 2 squared is equal to 4. Typically when you're writing an answer that includes a numerical portion as opposed to a variable portion, you are going to go ahead and do that multiplication out. If we have right here an exponential expression that is raised to a power, 2 squared raised to the 3rd, they call that the power rule. You multiply the exponents together. 2 to the 2 times 3 is 2 to the 6th, which again is going to be 64. What does this actually say? It says use 2 squared as a factor 3 times, which is 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6, which is 64. Don't do it this way anymore. Just use your power rule. Use your power rule. And if you had 64 to the 0 power, what would the answer be? What would be 1? It doesn't matter what the value is. If it's raised to the 0 power, the answer is always going to be 1. Okay, there. Now all of my A&M fans are just breathing a little bit easier because getting rid of all of this orange for UT. But you know what? I just do not have the maroon for all of those Aggies, so I'll just have to keep using my orange. Now, let's think about what happens. I told you before that yes, you will have negative exponents, 5 squared divided by 5 cubed. Well, according to our quotient rule, that's going to be 5 to the 2 minus 3, which is equal to 5 to the minus 1. And that looks strange to you at first, because you've not been accustomed to working with negative exponents. Well, just for grins, just for grins in algebra, not groans, grins, just for grins, let's see what we actually have here. We have 5 times 5 divided by 5 times 5 times 5. And we're going to cancel common factors now. 1 pair of 5s, 2 pair of 5s. There's still a factor of 1 here in the numerator. So we have the result of 1/5. Solved this problem 2 different ways. We first solved it in exponential form using our quotient rule where we subtracted the exponents. We got an answer of 5 to the minus 1. Secondly, we said, okay, I don't recognize what 5 to the minus 1 is. What happens if let's just go ahead and do this in expanded notation. So we showed 5 used as a factor twice in the numerator. Then we showed 5 used as a factor 3 times in the denominator. Canceled our common factors and found out that we had a result of 1/5, which we were a little bit happier with because we at least recognized 1/5. Both of these are totally legitimate ways to solve the problem. We have 2 different appearing solutions, but these are the same different ways of expressing the same value. So what does that mean to us? That means that, let me see, how do I want to show this? Okay, I really don't like doing it this way. X to the minus what? A. A is any real number and x has to be different from 0. X has to be different from 0 because we cannot have a denominator of 0, because we know that division by 0 is not an operation that we're able to do. The exponent is allowed to be anything. Now let's just think, this is the algebraic definition, if you will, of what happens when you have an exponential expression that is raised to a negative power. Here we have an exponential expression raised to a negative. Let's do it that way. Make it correct. Here we had 5 to the minus 1, 5 to the minus 1, 1 over 5 to the positive 1. The x here would be 5. This it would be minus 1, changed to plus 1. What this is saying is if you have a variable that is raised to a negative power, my daughter saw it this way. Someone told her that what you can actually do there is you take your base, we have x, 1 over x. x2, anything to a negative power, it's the reciprocal of that to the positive power. And I know that's not real nice and neat and cleaned up, but either think that when you have a base raised to a negative power, like x to the minus 2, you're going to change that into what is the reciprocal of x to the minus 2? Well, it's 1 over x squared. Or you just flip it and it becomes, here we have x to the minus 2 following this pattern would be the same as 1 over x to the positive 2. It's awkward, strange sounding. Try a few of these, and as you practice them, I promise you that they'll make a lot more sense to you. So let's go ahead and do now these examples that we have on page 94 of your text, and see if we can practice with some of these rules so that it makes more sense to us. And then by the time you work on some homework, it won't be too bad for you. Example 1. Say that we have 1 over 2 squared times 1 over 2 cubed. This is example 3. Now, they show this, the way that you solve this, in a very different way than I would show it, but we're going to do it 2 different ways. First, we'll do it the way they show you. Second, we'll do it the way that I would see as being much more logical to use. First, they're saying, okay, I have positive exponents in the denominator. I can rewrite that 2 to the minus 2 times 2 to the minus 3. From what we were just talking about just a moment ago, 1 over 2 squared is the same as 2 to the minus 2. 2 to the minus 2 is the same as the reciprocal of this expression, except the exponent is positive. 2 to the minus 3 is the same as its reciprocal with a positive. Now we can use our product rule. With the product rule, you simply add the exponents. That's 2 to the minus 2 plus a minus 3, which is 2 to the minus 5. We're going to use our definition that tells us that if we have a base to a negative exponent, that we can rewrite that as 1 over 2 to the 5th. And that's how they're raised. Can't see. Okay, that's how they arrived at their solution. Why did they go from 2 to the negative 5 to 1 over 2 to the 5th? Because very, very frequently you're going to be given restrictions on your solution that say use only positive exponents. So you just use this conversion in form to eliminate the negative exponent, show it as positive. Now this is what I would do. If I saw this expression here, I would say, okay, 2 rational numbers. Rational numbers are those that look like fractions. How do you multiply fractions? Well, you multiply the numerators and you multiply the denominators. 1 times 1, whoa, 1 times 1 over 2 squared times 2 to the 3rd. What does our product rule say? It says that if your bases are the same, you add the exponents. And obviously, we have the same answer here. I've shown it to you both ways. You will have to understand how to manipulate negative exponents. You will have to be comfortable with moving variables from the numerator to the denominator of a rational expression. But you don't always have to recreate the wheel. I mean, you learned a long time ago how you multiply fractions. Either one of these 2 ways works just fine. Let's see what we have next in example 4. We want to simplify 1 over 4 squared. 1 over 4 squared divided by 1 over 4 cubed. Once again, they're going to go ahead and change to negative exponents. And I really believe that the reason that they're doing this is just to give you practice working with negative exponents, because that's the title of section, whatever we're in, 3.3 of section 3.3. when you divide exponential expressions that have the same base, what do? You subtract the exponents. 4 to the minus 2 minus a negative 3 minus a negative is addition. 4 to the negative 2 plus 3 becomes 4 to the first, which of course is 4. Okay? Let me show you an alternative way to do that. How do you divide fractions? Sure. When you're going to divide a fraction, you multiply by the reciprocal. 4 cubed over 1. This becomes 4 cubed divided by 4 squared. You can subtract the exponents, and you end up with 4 for your solution. Once again, either of these two ways works perfectly fine. If they specify that you use negative exponents to solve it, I would use it this way. I'm not aware of hardly ever you running across something where it specifically says use negative exponents to solve it, but I guess you could. So what this is showing you is that very frequently you have more than one way that you can solve a problem. Let's go ahead and look. We have 2 more examples, but I want to go ahead and go through both of them. This is review for a few of you. It's not review for some of you. So I want to take the time to illustrate each of these exponent rules that we have. We have example 5. And this is the power rule, and it says to simplify this expression. We have in parentheses 1 over 5 cubed raised to the 4th. How can we write this with a negative exponent? And do you also see that we're just using the reciprocal and changing the sign? So the reciprocal of 1 over 5 cubed, the reciprocal would be 5 over 1. Changing the sign, that would be 5 to the minus 3 raised to the 4th. So what does our power rule say? It tells us that if you have an exponential that's raised to a power, what you need to do is multiply the exponents. So you have 5 to the minus 12. We want to give our solution using positive exponents. The reciprocal of 5 to the minus 12 is 1 over 5. We change the sign on the exponent, and we have 1 over 5 to the positive 12. How else could we do this? We could also realize that what this is saying is use this entire expression as a factor 4 times. So you have 1 over 5 cubed. If you're going to use this rational expression as a factor 4 times, then your numerator is used as a factor 4 times. Let me go ahead and rewrite that. Numerator is used as a factor 4 times. Your denominator of 5 cubed is likewise used as a factor 4 times. We use our power rule. 1 to the 4th is 1 times 1 times 1 times 1, which is 1. We have 5 to the 3 times 4 is 1 over 5 to the 12th. I do not care which method you use to solve these exponentials. You have to understand the method that you're using, but it makes no difference to me which one you use. Okay, one final expression, one final example that I want to go ahead and work through. And simplify this. 1 over 3 to the 9th to the 0. What's the solution? Exactly. The solution is 1. because it does not matter what you have contained inside the parentheses here. If it is raised to the 0 power, your solution is always going to be 1. So go ahead and play with your homework, section 3.3. The more that you work with negative exponents, I promise you, the more comfortable you'll be. And I'll see you next time.